Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel we cover all things Gen Chem related. On this video, I'll be discussing how you can determine the polarity of a molecule based on the geometry that the shape that it has taken on. Let's get started. We learned about polar bonds back in chapter 9. If you don't remember, make sure you guys go back to my previous video to learn about how to predict if something is polar. Just a real quick recap. Polar means that there are uneven sharing that's occurring between the atoms that are found within a molecule. So the electrons, although they're being shared, there's a covalent sharing of those electrons, they're not being shared evenly. The atom that's more electronegative is pulling the electron towards it. And so as a result, the electron cloud that's surrounding that molecule gets distorted. And so you have one end that has a slightly more negative region, one end with a slightly more positive region, and that result is what we know as a polar bond. Well, when we're dealing with a molecule, we're not only just looking at the bonds, whether or not it has polar bonds, that is a prerequisite, but we're also looking to see, when we look at the central atom and what's surrounding the central atom, the bonds that are pulling on it, are they pulling symmetrically? So if they are, you can have polar bonds present in a non-polar molecule. But in order to have a polar molecule, you have to have those polar bonds, so that difference in electronegativity has to be present, and you have to have an unsymmetrical shape that's created, or unsymmetrical pull that's happening on that central atom. Now, this is really important, especially when we get ready to head into chapter 11. The polarity of a molecule, the molecule is going to determine the different intermolecular forces that are present. So intermolecular, break that word down. Inter means between, molecular, so between molecules. And there's these attractions that are going to be allowing things to come together or ultimately try to stay away from each other. The polarity is also going to be determining things like the boiling point, the solubility, the melting point, and some other things that we're going to delve into in much later chapters. And so two things that are going to affect the polarity of a molecule, like I said, is the presence of polar bonds and an unsymmetrical pull that's occurring on that central atom. And just note, just because you have lone pairs on an atom, on a central atom, doesn't always mean that you're going to have polar molecules. And we'll talk about some situations and how you can look out for that. Okay. All right, so again, just revisiting this polarity idea, remember polarity happens because you have uneven pulling between the atoms that are present. And so in the case of like HCl, we know chlorine is far more electronegative than hydrogen, so it's pulling those electrons toward it. And so you can see the electron cloud is now distorted. You have more electrons found closer towards, or more electron-rich region found around that chlorine compared to the hydrogen. So you end up with these pseudo-negative and positive regions respectively. So we're looking for polar bonds, difference in electronegativity. Now, just because you have polar bonds present, like in the case of carbon dioxide, where you have a difference in electronegativity between carbon and oxygen, when we look at what's happening on the central atom, well, even though each of the oxygens is pulling the electrons more towards them, the pull is happening symmetrically. So I don't have an overall shift happening one way or the other. And so look at the electron cloud. It's nice and evenly distributed. And so what this tells us is that this molecule, there's no net dipole that's created, no region that has more electrons kind of hovering there or not. So this would be a nonpolar molecule. Okay. However, something like oxygen, which ends up with, again, those two bonding regions surrounding that central atom. Well, now notice in this case, we don't have, remember, if we think about the electron geometry here, remember there's these two lone pairs, and then we have those hydrogens present. Well, when we look at the molecular geometry, what we don't have is anything that's balancing out the pull on that side. And so what we have is this oxygen is pulling these electrons towards it away from the hydrogen. And so you have this really electronegative region, this really strong negative region created around the oxygen versus these positive regions created around the hydrogens. And so we do have a dipole present here, unsymmetric pulling. And so we would say that this molecule would be polar. Okay, so how do we go about predicting the polarity? Well, think about that progression. We first still need that Lewis structure. And then ultimately, we're going to determine the electron geometry followed by the molecular geometry. Remember, count the lone pairs, the bonding regions to get your electron geometry, redraw the molecule without those lone pairs, but keeping everybody in the same orientation to get the molecular geometry. I cannot stress to you enough, do not try to predict the polarity from the Lewis structure. The Lewis structure, the way we're drawing it, especially like think about water, right? If you look at the Lewis structure of water, you may say, oh, okay, well, there's even pool, they're straight and in line. But that's not showing us the angles that these bonds are at. And so you have to look at the molecular geometry to make this prediction. You then determine, do you have polar bonds present? And if you have polar bonds, you also look to see if there's that unsymmetric pool that's present on the central atom. If it's unsymmetric pool, then you would indeed have a polar molecule. Okay. So let's take, for example, ammonia. We've seen this structure a few times. We know NH3, if we look at the Lewis structure, will look something like so. We would look at the electron geometry and say that this should be tetrahedral because there is one lone pair, 3 bonding regions. So we would expect that tetrahedral shape. The molecular geometry, though, would end up being trigonal planar when we redraw without that lone pair present. So the lone pair would be here for tetrahedral. The molecular geometry would look like such. We do have lone pairs, we do have polar bonds present, that pull happening towards nitrogen, but nothing counterbalancing it at the top. And so if that's the case, then we would say that this indeed should be a polar molecule. Okay. And so again, this is just showing you can do a calculation if you know the electronegativities, but kind of the general rule of thumb, if you have 2 different atoms, more than likely it is a polar bond. Few instances where that's not the case, but I would say 99% of the time it's going to be the case. And so overall, we would end up saying that this is going to be a polar molecule because, again, we have this overall net pull towards the nitrogen, nothing stopping it going upwards. And so indeed, this would be a polar molecule. Okay. And so now let's try predicting whether these would be polar or non-polar. Again, we do not look at the Lewis structure. We got to think about, well, what geometry would they have? For the N CLO, we would know that we have 1 lone pair, 2 bonding regions. And so we would predict that the electron geometry would be trigonal planar. The molecular geometry would be bent. We do have electronegative difference in electronegativity, so we have polar bonds. And so overall, we would say that this should be polar because we don't have that symmetric pull. For the SO3 example that's shown here, SO3 2-, in this case here, we would have 0 lone pairs, 3 bonding regions. So this would be trigonal planar. For both the electron and molecular geometry. And in this case here, we do not have different atoms that are surrounding the central atom. There's the double bond there, but that just means it's pulled a little tighter, it's a little shorter, but it's still the same atom. And so overall, we have polar bonds, but we do not have an unsymmetric pull. And so we would say that this is going to be nonpolar. Okay. So again, you can see that breakdown here where we have a polar molecule, we have that difference in electronegativity versus our nonpolar molecule. Okay, good. Now, again, we're going to get well into this much more in chapter 11, but the reason that we care about this polarity idea is because this really does affect a lot of different properties. One of the main things that it impacts is whether or not things will interact with each other. If you've ever heard the saying, like dissolves like, that's what's known as the chemist's rule of thumb. That is based on the fact that things that have similar polarities will want to be around each other, like dissolves like. Things that have different polarities do not. So if you have a non-polar substance and a polar substance, those 2 things do not want to mix. And a great example of that is oil and water. If you've ever seen oil and water, we know that there's this layer that's created because you have this distinct separation. Well, that's because those two things don't want to be around each other based off of their intermolecular forces that we're going to learn in chapter 11. If you've seen makeup remover, something like the Garnier micellar water, where you see that distinct layer on the top compared to the bottom. Well, again, that's there because you need that oily substance to help to remove the makeup that's waterproof, but that water that also helps to ultimately rinse your face. And so this concept of like dissolves like, it's everywhere. It's even used when we think about how we dissolve the acetone off of our nails, or how we use paint thinner to get paint off of our walls. It's that idea, this like dissolves like, where you're looking to match polarity, different polar substances to be able to interact with one another, or different non-polar substances to interact with one another, okay? So I hope this video helped you guys understand how to predict if a molecule is polar or non-polar. Make sure you guys like, comment, and subscribe, and let me know what other information you would like to see. Come back and see more videos, and I'll talk to you guys later. Have a great day. Talk to you soon.